and this is what I actually did, move from doing a little bit of hardware long time ago to the dark side of software. And as Manoli said, in the last years, I've been doing a little bit of looking at RIS5. So with this background, you can see that out of the title, my background on AI is Epsilon. I know almost nothing, and I'm going to talk about it, okay? Hopefully, with the hope that maybe there are some things that we can leverage from the original background. And also, as you said, in this semi-retirement kind of thing, is just going to be, it's like grandpa telling stories from he was in the military service, and or maybe religious things or things like that. So it's going to be my personal opinion, and this is a real disclaimer. So it's nothing of what I say is official's BSc position. Okay, it's only myself, and this is the good thing of being fellow is I don't report to anybody. Nobody reports to me. I do what I like. I say what I like, and you'll have to bear with me for a full hour. Maybe I should. I don't know. I could make it longer. I'll try to make. Let's see. You'll have to bear with me. You'll have to see a few Paraver views, maybe a few hundreds, but don't. I mean, you'll survive. Okay. So let me start just with that background. Yes, I know very little about GPUs. Very little, or I still know very little about GPUs. And what I can say is at least with this kind of semi-retirement and steppings on the side out of EPI, during the last year and a half, I've been kind of looking a little bit more at that. And have I learned something? Well, one of the curious things is very curious, but we have between, let's say, the computer architecture and HPC type of thing and AI people, I think there's a big language gap and language difference. I mean, lexically is the same thing. So we talk about tasks, we talk about architecture, both about performance. Curiously, all these words mean totally different things in the two domains, okay? For example, performance to me means something where it's 1 over time, how the shorter the better. For them, and them I mean AI people, performance means how good is the answer that the system gives you. So we have really very different. I also feel like, as you said, very different from most of the HPC people in that I try to look at very micro or relatively microscopic scale compared to what most of the people in HPC does. Certainly everybody, well, I don't know, but everybody certainly everybody at BSc and those who are AI guys, they look at much more macroscopic things. So with these differences, what I tried to do in this period was to try to join a little bit with them and try to use and analyze a little bit of their codes with this, well, I tend to see what means happiness in those communities and in our community in terms of what percentage of peaks of the utilizations of the resources you use, with what level of performance is people happy, what is the level of performance that this is achieved in AI infrastructures, and back to co-design, is there room for, are there questions that might be interesting to look at and that we could learn or leverage from GPUs, or see if there are other ways of doing things. And of course, I couldn't do it but with Paraver. So the idea is what we started, and this has been presented last week at Cluster. There's a translator. Actually, we take NVIDIA Insight System traces, maybe, so probably you have used it. Insight System traces, we translate them to Paraver with the claim, I strongly believe, that Paraver has a much more scalable and much higher analytics capability than what you have with with Insight systems. I guess you have used Insight systems. How many people has used it? For 1 GPU, for 10 GPUs, for 100 GPUs, and I've not gone much beyond 100. Okay, but this is the idea: is try to use it and I believe that we have browsing capabilities that are relevant. And in reality, the whole talk is just a few tales, a few stories of my experience, how I went through this thing. Okay, and the tales are something like that, and there are quite a few of those, and I have slides for those, all of those. I mean, I have just 100 slides. I probably have no time to go through all of those. But and I don't know if any of you is interested in more or less on any of the topics. If not, I will try to go through some of those and try to tell a little bit my story. I mean, well, let me start by what happened when I tried to start looking at AI. So met with a team at BSc. They were doing training, fine-tuning training of full fine-tuning out of a Llama. They started with Mistral model. They went to Llama, and well, the idea was to look at it. How was it behaving? And these were the first traces that we saw for a run on 4 GPUs. And you see the different 4 GPUs, essentially each of these stripes here. You see things like, for example, you can see the link to the syntactic structure. Red is the forward step, white is the backward step, and they are synchronized. Of course, this is representing something like 20 seconds of execution on 4 GPUs. Okay, so it's a large scale, it's a real run on a real infrastructure on the Mare Nostrum 5, so H100s. And we can probably zoom at that and see the typical view where you see the sufficient granularity, detail of granularity, and this is somewhat similar to what you will see with Insight systems, okay? You see the threads activity, you see the streams activities, the colors in the threads represent the CUDA API call, and the colors in the streams represent the CUDA kernels. And in a sense, maybe one of the things which to me is interesting also is how it look, the lines. This is slightly different from what you see with Insight. Insight systems is a little, to my taste, is a little bit difficult to correlate a given launch with the execution of the kernels. And here you see, I think you see it more nicely, this kind of vision or activity of the main thread launching and spawning many kernels, which end up being executed later. It looks like to me to a little bit the task-based kind of model where you instantiate tasks. Unfortunately, from my point of view, with the syntax, with an API interface, which is not to me and the best way. But this is the kind of things, I mean, Kalia, this is the kind of things you were doing where you were at BSc, I think. Probably from the code design, I think, and we did present that at NVIDIA, I think we failed in terms of really making it forward. I think probably it's something that would have been nice for everybody, for the community. But there's a relationship which I think is kind of nice, and I don't know when even from what you say about this thing of global kind, I don't know how it's called now, the joining the two architectures, the ARM and the RISC-V, and this is actually co-design. How much we want to go into the real traditional. I mean the CUDA-like type of loading or heap. Okay, ARM, AMD having to follow NVIDIA. I don't know. That those things are to me co-design kind of questions. How do we want to go in this way of expressing the concurrency and instantiating the work? anyhow, you'll see there are going to be many of these very, very general things which one might want to enter, and to me are co-design, but I'm not going to enter really very much. Well, I've taken out the activity in the CPUs. I can take out the activity in the GPUs, sorry, the launching lines, and I can see only the activities in the streams. And one of my issues when I tried to look at it was, I understand, and I don't know what you think of that. I understand there's a common wisdom, people saying AI is communication intensive, right? And I understand NVIDIA did NVLink because of that. And so I try to look at that. And what do you see here? Look at the kernels. The blue ones is nickel. The blue ones is the communication kernels that happen to be on different streams, but these are the nickel kernels, the communication kernels. So the answer is yes. AI is very communication intensive, right? So next slide is you take out the nickel kernels and you look at the compute kernels, right? What's the percentage of idle time between all of these compute kernels? Epsilon, 3.5% of idle time. So the reality is that for this execution, for this run is at all communication, not at all communication limited, okay? This is just compute bound, right? And I don't know where and to what level is people going to use. Is at 4 GPUs that is, you can claim, oh, it's going to be, but maybe at 100 GPUs is going to be communication bound. Or at 1000 GPUs is going to be communication bound. And of course, the higher you go, it will be more, but the question is to what level and what amount of GPUs does people use in reality? And our guys, they use from 4 to 64, and that's except from some very special cases. Another thing is, okay, the second common wisdom is AI is matrix multiplies. You do a good matrix multiply accelerator and you are set. You've covered the AI. Okay, if you look at it, these are the kernels that are gem kernels. So it's only 50% of the total compute time. We are at the point that with under load, you can make a perfect gem accelerator. Okay, you will speed up 2x compared to what we have today, period. So we have to look at something else also. We have to look at other kernels which are non-gems, and we have to try to look at some of those. I had more questions. I'm going to speed up because this speed I'm not going to the 100 slides. Some of the how do we handle those things in terms of their individual performance? But in terms, very often there are element-wise operations. So there's very memory bandwidth intensive, one after the other. So fusion, this kind of fusion, and people does fusion, but probably there's a need for much more of that. And there's actually, from my point of view, an architectural question. How much is fusion supported by GPUs, or how much fusion is supported by a RISC-V like ISA, okay? And I don't know what you think. My belief is that fusion, you can do it, people does it. I think many of those things is a pain. Really programming the GPUs at the end, the bottom is a real pain. Some people does it, and of course, very, very great performances, but I think they're interesting things and questions and directions in terms of ISA and the availability, the capability of the ISA to improve some of these things. More things that can be obtained with the tool. You can look at hardware counters. What is the number of SM actives? So for example, this is the line of 100 would be around here. Okay, so most of the SMs are active all of the time. If you look at the instruction issue rate, the IPC, okay, it's kind of less than 50%, some spikes going to 50% of peak. If you look at the utilization of the tensor cores of the real horses for computing, it looks like around 50%, okay? If you are doing memory design, and I don't know what you think, just look at this, and the read bandwidth of DRAM, again, looks like 50%. The write bandwidth, what is that? Maybe 20% of the peak. What is the design of the systems? And if you do a RISC-V system for AI, how should you balance those things, okay? How should you balance your read bandwidth? Is your read bandwidth equal to your write bandwidth in the system, or maybe you have alternatives that are more economic? And that was with 4 GPUs. What happens with 100 GPUs? This is 100 GPUs. You see the same thing. Kernels, you see all the hardware counter metrics, the variability of those things, and actually you can zoom in and you can see the detail, and you really see that the way they were running it, those metrics that you would ideally like them to be at 100% at the top bar are, well, sometimes you have a lot of SMs that go inactive. Sometimes, well, tensor cores also. So there's potential to advance. The memory bandwidth subsystem utilization, you see those spikes, and the question is, can we, or what are the fundamental effects for that? So this was kind of the very first experience. One set of slides that I have here is about hardware metrics and what are the values that you see in a more aggregated way. Those were kind of just timelines, evolution of time. And where's Vasilis? No, the other Vasilis. Yes, you don't like it, or you. So what I just want to show is a little bit. Yeah, this is the timeline. This is only 32 GPUs. You see the structure a long time, the structure, these are on top, you have the kernels, the color are the different kernels. At the bottom, the color represent, and this is for 32 GPUs, the color represents lighter color, lighter green represents short kernel duration, darker blue represents long kernel duration. You see the structure. And in reality, if you look at it, there is kind of forward and backward clear differentiation, but even inside the forward, there is kind of a structural differentiation. And the thing is, we are not only representing timelines, which is nice, is functions of time, and there's, at the end, I mean, this is to show colors, but this is the fundamentals of Paraveris. You deal with piecewise constant functions of time, and it's a full algebraic kind of model and methodology to define your own new metrics. But you also can do histograms. For each of those metrics of time, I have 5 metrics of time for which what we have done is we've taken out the time dimension and we do a histogram. And these metrics go happen to be efficiencies between 0 and 100%, so between 0 and 100%. And dark blue is the value at which there's most frequent value. And so if you look at active SMs, the first row, you see that, yes, you have many often, you have 100% of the SMs active. Sometimes you have, 85, whatever. Look at the tensor core activity. It's not always, well, very often very low, and not always totally perfect. Or DRAM bandwidth. What is the DRAM bandwidth that is obtained from the system? Is this the peak? Is this? So there's what I'm trying to suggest, that you can quantify the kind of information that most people use. Actually, most people gives the time. This is a little bit finer detail. Is for the metrics and given the individual values and the histograms of those individual values. And you can say this is for one of the phases that I identified. Are all the phases similar? Are they different? So this is kind of, well, I did some annotations on what you see, but it's mostly what I commented. And you may like the values or not. This is the animation. What happens between phases? Different phases. Again, the message is potentially there is room for improving, maybe, probably. And there is the metrics or ways of measuring that can identify or tell you directions or places where you might want to look at the alternatives for improving. Otherwise, the reverse, if you look at EPI, for example. So here you see what's the percentage of tensor cores that you get active, and can we do on the RISC-V vector get to not 75 or not 18 or 90 utilization of the vector functional units, but getting to higher values. And well, there are things that one can actually compare between the two approaches. And one of the things I wanted to compare is histograms again. This is not different. Each of these things is not different metrics for a given run. These are four different runs, and it's the same metric, and it's a histogram of the metric. So this metric is, for example, the duration of the kernels. How long did the kernel take to execute? So I don't know what's your experience, what's your feeling. How long are the kernels executed on a AI run on GPUs? And if you look at the histogram, there's the biggest place is, this is about close to 5 milliseconds. Most of them are in the 2 something here. There are many of them that are in the sub microseconds, certainly in the microseconds kind of range. Okay, there's a histogram, and then you can do for codesign the typical things, and you can start thinking what would be the impact on things like, for example, kernel launch overhead. So you take a function of time, which is kernel launch time, you build a histogram of that, and what is the histogram of the kernel launch phase is this thing. What does it tell you? Between 0 and 50 microseconds, this is the duration of the different kernel launches. Most of them around 5 microseconds. Okay, this is the characteristic of the GPU. You can measure other things like, for codesign would be, and what is the time between 2 kernel launches? Okay, the histogram of the time between 2 kernel launches, and this is up to 3 milliseconds. So one could zoom here. It's most of them is very back-to-back kernels, but sometimes that's not the case. So just wanted to show a little bit to introduce the thing. One can obtain histograms. It's a very simple analytics thing. It's a thing that tools don't support. And it's very interesting. And the other good thing is this gives you the histogram, but the histogram is not the whole thing. You can say, oh, which are the kernels that take around 5 milliseconds? And you can, from the histogram, go to the timeline, and you can see in the timeline, you can see those kernels. Do they happen all of them at the same time? Are they skewed? Is there a periodic pattern for those kernels, only for those kernels? It's the kind of navigation on the data that I strongly believe you have a lot of difficulties to do with Insight systems. And from the philosophical point of view, there is one thing. So if you look at RISC-V vector, what is the latency launching? What does a launching a kernel mean? Is a order of cycles. Okay, what have we seen for GPUs? Is of order of 5 microseconds. Okay, big difference between the two things. What are the granularities? But if you look at the ratio between the launch latency of the operation and the execute time of the operations in API, you launch an instruction which takes 32 cycles to execute. Okay. On the GPUs, you launch an operation, and most of them are less than 150 microseconds. So one thing to me is curious is the ratio between those numbers, and I don't know. I tend to think that there is something magic in the number 30. Okay, which I don't know. Is this a fundamental thing? Is this a cause of the things, or is an effect? By the way, when we started the first chip, what was the ratio, the performance difference between a scalar AXP and a vector ASP? The ratio in performance, the vector ASP was 30 times faster. Okay, there's something I don't know. Okay, and so I don't know if this is a law of nature or this is, but there is something curious. There is something that we all tend to that in order to justify a given program structure, we end up defining tasks of a granularity which is kind of 30 times higher than our launching overheads. Is kind of a curiosity, but maybe even more than a curiosity. The other thing is how these things can impact the programming, the structure of the programs, right? If you, instead of, you can say a GPU and RISC-V vector core are the same thing. The only thing is the granularity difference. One of them launches things in 5 microseconds to execute things of 150. The other is launches things in 1 cycle to execute them in 32 cycles. But do they give you the same opportunity to really get to 100% of utilization of your hardware resources or not? To really what we said before about fusion and reordering of computations is an interesting challenge. And this is what I thought RISC-V and RISC-V vector with long vectors, this was kind of the fundamental direction that should be or should have been exploited in order to try and compete on a different kind of philosophical approach to how you schedule and how you order computations and how you overlap those things and tolerate latencies. Anyhow, very philosophical. I strongly believe that, for example, the matrix extensions that are being proposed for RISC-V should be, and Mark Casas is actually pushing on that, and the standards, you may. Es una merienda negros. Anyhow, you don't know what will end up happening, but the philosophical thing I think is a very important, and we should try to push kind of the same philosophical approach that we had in EPI for those extensions. Well, I'm half an hour through it. This is one of the regions that I would skip. Are all gens born equal? I will skip that, and I will go to the load balance stuff. And the same as the AI equals matrix multiply. Is AI training having load imbalance or not? I don't know. When I asked this question to our AI people, they said no way, no load imbalance. Okay. When I look at the traces, look like this. So during these computation phases, you lose 23% of the GPUs because of load imbalance. Okay, on a run with 128, you lose those. And it's true, this is an effect that grows at 4 GPUs, there is not so much. At 128, there is quite a bit. Okay, and if you look at why is there load imbalance or where is load imbalance, you can build a profile of what is the duration of the different kernels. And this is what you see here, the profile of the duration. Every column is one kernel. If there is a homogeneous coloring across all rows, means that all GPUs take about the same percentage of total time. The darker the color, the more percentage of time. But what do we see? We see some kernels that are very homogeneous, which means they all take in all GPUs the same amount of time. But we see some kernels that take more time in some GPUs than others. If you build a histogram of that, this is the histogram. It says some of those kernels stays close to 0 milliseconds. Some of those kernels get up to 20 milliseconds. Okay. So, but very high variability across GPUs. Which are those kernels and where do they happen in time? You visualize them. They are happening in time here at this beginning of this phase. And they happen in different GPUs. It's a static repetitive pattern. It's always the same pattern on the GPUs. And what are they? If you look at it, is the attention layers inside the transformers. Okay. And there's more to it. I'm not going because probably it will come out a little bit later. So there is load imbalance. It can be significant, and so approaches to address that load imbalance. And should they be done at algorithmic level? Should they be done in the architecture? Let's see. Communication. How does communication look like? For the same trace, this is the kernels that are being executed. So a big hole here, no activity, a big hole here, no activity. This is the message sizes that are sent during those activities. Okay. If you look at it, there's big messages in this hole, not that big messages in some of the other holes. By the way, when we said before, nickel, there's a lot of time in nickel, but nickel and like MPI, every communication thing, MPI, all of those things is a gas. They fill whatever space you give them. If your program is in balance, you will pay that at an MPI call, synchronizing MPI call. Same thing here. If you give it space, the MPI call will spend a lot of time not transferring data, and then when the needed synchronizations are achieved, will be transferring the data. So if you look at it, even if there is activity in a significant, so kernels are active in a significant fraction of the time, comes out that the regions where there is communication kernels activity and no other activity, no computation activity, happens to be something like this, at maybe what, 10% for this case. So the question before is communication intensive important for 132.28 for 128 GPUs with this specific training and framework, and ends up being 10%, okay, at 100 GPUs. And one thing that when looking at this came out is, okay, you have this kind of very synchronous kind of patterns. What does that mean? There are global synchronizing collectives. Is it possible? Is there really real dependence between these communications and the computation that goes behind? And it came out talking to the guys is, no, we have just the framework enables us to ask before launching the job whether I want to overlap communication and computation or not. And we said no overlap between communication and computation. That's what they said. So what we tell them is, okay, maybe if you enable the overlap between communication and computation, you will gain 10%, right? This is what we tell them. So this is what we tell them. They did it. Answer. The answer was, if you enable the overlap between communication and computation, behavior is different, yes. Time is the same, right? Why? Well, if you look, and we have this kind of the pop metrics that we use. You have metrics like communication efficiency. We can quantify abstract metrics that quantify the global behavior. Communication efficiency is 90% here on this case. So we should be able to gain 10%. We should be. It's 90%. This kind of metrics tell you if you were able to do that perfect, communication perfect, you would gain 90%, 10%, sorry. You are 90, you are not 100, so you should be able to get to 100. Okay, we do it, and it does improve from 90 to 94. Yes, it does improve, but that does not reflect on the total performance. Why? We have other metrics. By the way, load balance improves also a little bit. We have other metrics, that there's an important one, computational efficiency. If you take this as a reference and you say, how much time did all the kernels execution take? So what do you expect when you overlap? This is with non-overlapping. What do you expect with overlapping? You expect the kernels take the same amount of time. Not true. When you overlap, the kernels take more time. So you lose kind of 7% because of the kernels taking more time. Same kernel, same number, identically. The thing is, you take the GPU, you overlap communication with computation kernels, those kernels take more time. I don't know how much people is aware of that. I have a short discussion with Mistral, and they have this feeling, yes, we have experienced that. We have not seen the whys, but we very often then don't overlap too much. We don't ask often too much overlap. How does reflect, instead of the global metric, instead of the microscopic histogram of the duration of the kernels? Same kernel in this case and same kernel in this case. Here it takes this amount of milliseconds. In the other one takes a few more milliseconds. Okay, the majority. I mean, there are some that take the same amount of time, but the majority, there's a majority shift. And by the way, it's not constant. Same kernel, different instances of the same kernel take different amount of time. So all these analysis of considerations of saying, no, I'm going to, AI is matrix multiply, I take a matrix multiply and optimize a matrix multiply, and I'm undone. There are many matrix multiplies, many different types. If you saw the colors before, there are many of those. And well, many, 5, 6 being used by the framework. And even within one of those matrix multiply, they take, and their variability can be relatively important. 15, 20%, or So it can be relatively important. So how much, or can we get to more understanding of this behavior? So what we did is, what we have here is, here on the left, these are two gem kernels, the blue and the green kernel, that execute back to back, and they execute back to back many times. So you take one of those times and you take one of the other times. Came out that in the very first time step, that very first instance that you take, the blue kernel takes less time to execute than the green one. At the end, the second one the blue takes more than the first, than the green one. These things are at the same scale, so the variability is pretty significant, is what we saw. Variability is pretty significant. And the reason is why. Why does this happen? Well, the kind of views that we have here, this is a view of where is nickel activity, where are nickel kernels launched. And you see that because of the imbalances, there are some nickel kernels that are launched earlier than others, okay? And this is in one iteration, this is on the next iteration. So nickel kernels are launched at different points in time. But what are those nickel kernels? Those nickel kernels are collective operations. What is a collective operation? Everybody must be there. So the thing is, and reality, what is the activity on the hardware link, on the MB link for those nickel kernels? So this is the activity on the MB link. You have burst of activity when the nickel kernel starts, a little bit of burst of activity. Then you have regions with no activity in the nickel kernel because you have not got to the synchronization point and the other guy is not ready and you cannot really do the communication. And then you have the bulk of the transfer, which happens while you are doing, everybody is inside the nickel kernel active. Okay, this is the behavior of the communication phase, and this happens in both of them, and you could really look at that a little bit more. The other thing that is also interesting is, by the way, the efficiency here is not that impressive in terms of using the percentage of usage of the MB is not that impressive, but this is the pattern. So does this pattern have an impact or a correlation with the duration of the gem operations? And these are two hardware metrics. This is a metric, and by now you will see dark blue is high value of the metric, light green is low value, timelines, and is the same thread, same. So what happens? This is tensor cores active. So what happens with tensor core active? Relatively high here, goes down the activity of the tensor core, okay, and stays down for a while. So there seems to be an effect, which, and so I'm just trying to tell you, we have the ability to try to dig down and try to identify what happens. I am ignorant about the real reasons, okay? I only can tell you that this does happen, okay? Which is when there is overlap between communication activity and kernel activity, the gems shrink their effective performance to 1/3 of the peak, to 1/3 of what they achieve when they are not, there is not that overlap. What is the real reason? And Filippo is not here. I've talked a little bit with him. I don't know how. What is the real reason? Maybe Filippo spiega. I've may have to do with the resources, the thread, the warps, the threads that have to be launched, the pre-scheduling that the hardware does. There is something that, if nothing else, is something that would be nice if NVIDIA looks at that. The other thing is, would be nice if you are doing a RISC-V thing, try to avoid these things, okay? So try to see what is the fundamentals of that and try to avoid those. So more things. I think I'm going to skip also this one. Sorry, this is about packing, and this is about we mentioned before the reason for load balance. The reason for load balance is actually because of this packing cost. When you have an AI model, you have an input sequence size, which is the buffer of the input, the number of tokens that you process, typically 8,000, 16,000, something like that. And if your prompts are not that big, you end up having to pick prompts, okay? To pick several prompts and pack them into the input buffer. And because of the computational cost of the algorithm is not linear, then that makes you have these imbalances. But the question I had here is, this is also another interesting question. What scares AI application engineers? Okay. The very first answer is none of the above. Okay, we're using a world where they say we have GPUs, we have NVIDIA's fixing it, it's perfect. NVIDIA tells us we do this, we do that, and that's it. So they are not scared about any of the above. What are they scared about? Out of memory. This is what scares them. Okay, this is how to dimension their problem. They only have the 80 gigabytes or whatever they have in the GPU, and they have to put all the data there. And this is what scares them. And essentially, how do they work? They start running. You run with a microbat size of 1. Okay, fine. You run it. This is the trace. You have a forward step phase and a backward phase, and you have a microbat size of 1. You can argue, oh, but I may not. The problem may be small. May not be using the GPU at full. So if I use a larger microbat size, the problem kind of the matrix multiplications, let's say, will be bigger. So I will be using more efficiently the hardware. Okay. And there is another thing which is an implication on the numerical on the performance from the AI point of view, on the quality of the training. Okay, so day one they are kind of obsessed with increasing the microbat size. What happens when you increase the microbat size? Doesn't fit. Okay. What happens then is they try to apply techniques. So among one of them is gradient checkpointing, which means in the forward phase, you keep going forward, but you throw away a lot of what you have already computed, such that when you do the backward phase, you will recompute from some of these checkpoints. You keep only part of the layers, and you will recompute the thing. And you will be doing this kind of recompute the forward, do backward, recompute the forward, do backward. This is the idea. But it's essentially throwing most of what you compute in the forward. And yes, you do that, and you can run to larger microbat sizes, okay? But to me, it's something that kind of hurts me, okay? Saying I'm just duplicating the computation for the sake of having a larger microbat size, to me, it's painful. There's no other way to get something similar and really to be able to deal with larger microbatches and don't duplicate the computation. And if you ask them what they tell you, well, this is only 30%, and who cares, right? I don't know. I would and for if you are working on memory, it would be nice to look at ways of doing that. Just one comment how I see that. This is the original trace, which means for microbat size 1 without gradient checkpointing. These are the kernels. And there is with gradient checkpointing, these are the kernels. There's a slight difference that you can compute, and you can see there are some kernels. These are the kernels which are executed when you do gradient checkpointing to essentially recompute the forward in pieces halfway through your backward. And this is the enumeration of the layers. There's one layer here. There's one layer here. By the way, you see some layers have this global collective open communication, which really, in this case, communication is more important. Okay, so it's all depends on your settings. When I said communication is not important, then communication is totally important. Then the only thing, my only point, and I said no, communication. I'm not saying so. What I'm trying to say is that all of these things have to be looked in detail, and very often are just blind for the AI engineer. Okay, they really don't look at that. They really don't care. And from my point of view, it's kind of painful. And if you look at this pattern, you really see that in the layers that have communication, this is kind of 22%. So it's not the 30% they say, it's less. Because in other layers, it's kind of 34%, 34% of the time. So if you were able to eliminate this communication stuff, and you were able to fix the issue with the overlap between communication and computation, and because this communication is not, there's no dependence, so could be overlap. The thing is that if you overlap it, it shrinks your CPU performance. If you were able to fix all those things, then the percentage would be closer to 34% than to 30% or to 22%. But in reality, 34%, if you correlate that with the number of, with the hardware content of tensor core operations, it comes out that this is kind of more like 40% of the total operations are done for. So it's closer to this totally duplicating the computation, which is the thing that hurts. By the way, it's kind of 40% of the tensor operations happen during this forward recomputation in the backward phase. By the way, only 5% of the NVLink transfers happen concurrently with this thing. Okay, so the only thing I mention is it. To me, it hurts, and it would be nice to really be able to look at the details and try to understand, try to look at it. Well, I can see. I will skip these things. I'm getting close to the end. Just the other thing, which I don't know what happens or not. So is for this problem, and this is related to what happens in RTM. Okay, reverse time migration. The kind of thing is you have a forward step where you do a computation, you produce a lot of data that you need to use later. Okay, and reality, this is a forward. You produce the data. Data, by the way, the data that you produce here, you reuse it there. So you have ages to reuse some data. So is there for memory architects, is there no way, I don't know, CXL or using, is there no way to really just, instead of totally forgetting the data, send it to a memory subsystem which has just enough bandwidth, very large latency, enough to avoid the recomputation. And people does things in software for this, okay, sending it to the host, but they are not really that much used. So to me, it's something that hurts a little bit. I don't know if people will be using more of CXL. I don't know if people will be, but working on frameworks to try and improve the current behavior of those that try to do it. Anyhow, these are kind of some of the stories that I went through this process of trying to understand about the AI behavior. It's curious how it's life in AI times is run. Okay, is Alice in the Wonderland, is the field, the people changes so fast, so much, and the typical answer, the typical thing is you're using a framework from 1 year ago. What are you doing? Okay, you have to use the next one, and then the guys spend a month to take the new one, install, update, and you run the new one, and what happens? Well, yeah. Well, by the way, it changes totally the kernels. So the gems, one of the versions was using one kernel, gem kernels, the other was changes a lot, not to change a lot, right? Essentially, the time is about the same. A little bit faster, yes, a little bit faster. But if you look at the fundamental, what for me are the fundamental problems that we have been looking at, same fundamental behavior. So I don't know. It will be important to look at these fundamentals and try to try to see what are the alternatives, and try to see what that means for EPI, for RISC-V. What are the things that by starting now, by doing it now, do you have choices to avoid? Of course, NVIDIA also has choices to improve, but at least is something interesting. So just to finish, a little bit of marketing. If you have runs cases that you want to look and analyze in POP, we do analysis of these things. So contact us and we can do analysis of runs of that, and trying to contact people who does for engineering application, for example, uses AI kind of programs and these kind of things. A little bit again about religion, which is scalability is not only about size, which is what everybody says. Scalability is about dynamic, from my point of view, is about dynamic range. And this dynamic range of being able to measure and look at microseconds, milliseconds, as well for the same run, and being able to shrink between looking at things at microseconds, even less than that, to milliseconds or even more than that. This ability, I think, is very, very, very important. Okay, and the other thing I strongly believe. I mean, and I know, for example, this is a comment for the architects doing Gen 5. I know the limitations, right? But really, you cannot simulate many of these things on Gen 5, okay? 100 GPUs running for 20 seconds. Okay, there's no way that you can do that. So the question is also important in this scalability is how do these things combine? We had presentations about some of these systems. How do these things combine? Okay, and a little bit in the direction of what NVIDIA does is can we get snapshots of the state of the system? Can we simulate from those snapshots small things when we know exactly what we are looking for? A blind search for things, I think, is too much. My personal opinion. Okay. So the final thing is, well, my motivation was to see, can we leverage, and this I think should be our interest, because AI is there and AI is going to eat everything. So can we leverage some of the background that we have in HPC to steer things and activities there? And I think that the tools, the tools and this scalable kind of analytic tools is really important, okay? And kind of steering, identifying what to look for and what direction to do the experiments, because the space is huge and we have to be a little bit steered a little bit, okay? So that was it. I hope it was not too hard to see so many parallel timelines, but that's what it is. You have survived, I think. So thank you for listening. Thank you.
So questions for our speaker?
Yeah. This is very interesting, Jesus, and sort of it shows the pain, and we can fully sympathize. We are going through similar stuff. So about the interconnect, right, for me, maybe a bit closer also to that area. So I'll just, so it seems that NVLink is basically completely unnecessary and a waste.
In this run, in these runs,
your numbers, and from what we understand, what's your, I don't know, how do you
thing that in these runs, it is. I didn't mention the detail. I had some that was more important or not. In general, I strongly believe that NVLink for running AI things is something that has probably been done for the big players. If you run with 100,000 GPUs, right, there you may have more importance of the NVLink thing and less capacity to handle it with proper overlapping of things. But for many of the runs that most of the mortals do, I think is a little bit is a little bit of an overkill. Of course, now that you have it, it's this thing like the 30 magic number. Once you have it, it's something you never know if it's a cause or if it's an effect. It's going to, or it can influence the way people programs, okay? But to what I seen is not always that needed. That's my perception. And I've gone to 128 GPUs. I've not gone to 1000.
Thank you. Thank you.
So, Jesus, you are a Pythagorean mysticist, probably. That's why the 30 ratio or something, right? Do you think that this type of approach can be, shall we say, carried over to the vector world? Using vector processing, you mentioned yourself this, shall we say, interest that you have there. I know the tools can be applied, etc., but what would be, let's say, the equivalent of I don't know, a collective in that environment? Would it be the gather operations, for example, and such?
The operations that you have to do are typically what they do now, and they are all collectives, and essentially everything is collective. So I'm not sure they will change it, or that will change easily. So the comparison with the RISC-V is, to me, the comparison between EPI and GPUs, how one should think of that comparison is one RISC-V vector is equal to one SM. To one SM. Not even the kernel, no, to one SM.
The SM itself.
To one SM. Which means the GPUs have a kind of, the kernels have several SMs working for the same kernel. So there's a hierarchical thing in this task-based model. There's a hierarchical thing that makes big tasks out of what actually the different SMs work, okay? So this hierarchy, in terms of architecture, I think this kind of hierarchical support would be important. And then the thing was, in terms of the communication between these devices, I think is not going to be different from what is the NVLink? Is you have a NIC kind of thing, you have so it's communication is always the same. So it will always be the very same thing. What I'm trying to say is that probably we have been rushed by NVIDIA, and now everybody talks about warps, and everybody talks, which I hate that. But so we have been overrun by a way of doing the things. I do believe that you can get the same things with closer to a traditional approach, and that's what the vector architecture in essence is.
And we have seen that we can do quite efficient, shall we say, kernels with a vector unit, right? But I don't think we yet have the whole structure where we can run the workloads that we run on NVIDIA, for example, right? Do we have the whole edifice?
Well, the frameworks, I mean, we have that. Mark Casas has that working. So he downloads from Hugging Face something, the code, the data set, the whole thing, runs Python stuff, and he runs that on the SDB. Of course, with a memory of a few gigabytes, with a tiny model of thing, but runs, and it's nice, it's fun because you see it, and it's such a small model that when you make it you ask a prompt, and what it tells you is, well, apart from the hello and these kind of things, what it tells you is just crazy. But the whole thing, the whole framework runs. So doing the system, I think is a matter of applying the traditional NICs architectures, the traditional things onto a clusters of RISC-V, which, and if you tell me, can it be a single node with just physical shared memory, or can it be kind of on a several chips sharing memory, or not? All of this, but to me, it's like the common architecture. All of this is there. It's already there. I mean, we don't have the prototypes, and if we had the prototypes, you would be able to demonstrate many of those things. I don't know if I am very optimistic or.
I think you are pointing a way, which is important. Questions for the audience, for the speaker? More?
Thanks a lot for insightful presentation. Do you think that there would be a difference between inference and a training? Because as I see it, there would be different communications and a kernel's calls. So that would be a different behavior between the inference and a training. And that may be just, result in a different code design, right?
Yes, there may be and I have in the slides. I don't know how to do it. In the slides, I have some. We have looked at some of the inference. By the way, the inference at the level that we do it is an inference with just one GPU, because the model fits and the inference. And there's a lot also to learn about the inference. Of course, granularity is much finer grain. Here, people does not use CUDA graphs. There, they have to use CUDA graphs to reduce the overhead. So the things change, and you might have different optimized co-design points, but my belief, and I know that I go against most people, I believe that a good architecture should be able to fit 90%, 95% of the use cases, the architecture. The actual implementation within that architecture, whether you use a vector length of 16,000 or you use a vector length of 8,000, or whether you use the actual implementation, something that might be tuned. But I like to also make a difference in that, from that respect. In the same way that you can have a RISC-V vector, you were saying the couple thing. So you could have a non-homogeneous shared memory system with homogeneous, not homogeneous, but so RISC-V cores, some of them be RISC-V vectors, some of them being RISC-V scalar. The architecture, or even having different vector lengths, the architecture should be not that different from my point of view. Maybe I have too much or ambition or too much, but I think that's what would be nice. The implementations, true, you can tune them and adapt them to really the specific things. But if you say, for example, CUDA graphs, inference, CUDA graphs, why did they have to use CUDA graphs? Because the overheads were killing them. Kernels were so much smaller than this one, the overheads were killing them, so they had to do CUDA graphs. In a sense, if you think of EPI, it goes in the direction of our overheads to launch a kernel is a few cycles. And the kernel is, so maybe the architecture is still valid and really tolerates that kind of finer granularity. There's another thing which I think people looks at that inference. To me, that's one curious. In inference, if you look at people increases batch sizes, okay? To have large batch sizes to say, in this way, I'm going to get better utilization of the GPU resources. If your individual devices were not as the whole kernel or like a large number of SMs, but you wouldn't have those kind of problems in the architectures that we were mentioning. You wouldn't have those kind of problems. One of the curious things I have seen today in GPUs is you increase batch size, things get better, yes. But at the end, also saturates. And what saturates? Is the host. Is there's between every token and every other token, you have a lot of time in the host and people does not use, I don't know, there's opportunities to use the multiple cores in the CPUs today in our system, because I mean, it's kind of funny, but we have systems with 40 or 80 cores driving 1 or 4 GPUs and 60 of the cores are idling. This is kind of, and so these kind of things still is within the same architecture, but better uses of the systems and not always on the device side in terms of architecture. I think it can also be in the side of the kind of hosting, which I'm actually against about hosting. I'm more on an homogeneous. Sorry.
Put the slides up again.
No. I think, well, I don't know.
Is there a question from the remote attendees or comment?
All slept.
No, thank you. Thank you.
Okay. From the room, someone else to ask questions? Okay. Thank you very much, Jesus.
Thank you.